When we say combining functions, what we mean is that we can operate on functions, meaning that if I were to give you two functions, you can add them together, you can subtract one from the other, you can multiply them together, you could even divide one by the other. We know that you can do this on real numbers already. You can take two real numbers, you can add them together, and your sum will be a real number. You can subtract a real number from another real number, and your difference will be a real number. You can multiply two real numbers together, and your product will be a real number. And of course, you can divide a real number by another real number as long as it's not zero, and your quotient will be another real number. Well, similarly, you can do this on functions. You can add two functions together, you can subtract one from another, you can multiply, you can also divide. So to get us started, allow me to give you two functions. All right, I've given you two functions. I've named one of them f and the other one g. Now keep track of these two functions because we'll be using them a lot for the next couple examples. Now, if you notice, function f is a linear function. It's written in mx plus b form. The graph of function f, would be a line with slope positive 3 and y-intercept negative 7. While function g is a quadratic function, so we know that its graph would be a parabola. A parabola, in this case, opening upward because the leading coefficient of this quadratic function is positive. So what we're going to do first to get us started is we are actually going to find a function value. Now, when we say find a function value, that's the same thing as saying find a particular output. I'm going to ask you to find an output. In order for you to find that output, I'm going to have to give you an input. So here is the first thing I'll ask you to find. F plus G at negative 2. Basically what this notation means is I want you to find the value of this function. F plus G is the name of the function. Find the value of that sum function at negative 2. In other words, negative 2 is your input. You find the output. So the way this plays out is pretty straightforward. You're going to want to take negative 2 and you're going to want to plug negative 2 into f and also plug negative 2 into g and then add your results. So something like this. F at negative 2 plus g at negative 2. So notice with my notation what I mean is we're going to plug negative 2 into f first. We're also going to plug negative 2 into g. And whatever we're getting as a result, we will add. So plugging negative 2 into f looks like this. 3 times negative 2 minus 7. Right there is my work for plugging negative 2 into function f. Don't forget we need to add that result to my result that I get when I plug negative 2 into function g. When I plug negative 2 into function g, it looks like this. Negative 2 squared plus 2 times negative 2. Let's continue with this arithmetic. So this is what? Negative 6 minus 7 plus, and then negative 2 squared is positive 4, and then 2 times negative 2 is minus 4. Let's continue. So then this gives us negative 13 plus 0. Let me move the screen up a little bit here if I can. There we go. So then to finish this off, you can see that the final answer is negative 13. This is the function value. Let's see if I could zoom out a little bit here so you can capture the entire screen here. If I can here. Bear with me. Okay, I managed to zoom out a little bit. This is the entire problem. So you can see we were given function f and function g. We had to find the function value of this function f plus g when the input is negative 2. Now, I just want to kind of remind you that negative 2 is your input. It's what you plugged in. and negative 13 is the output, or we like to call the function value. All right, I'm going to give you another example using function f and function g again, okay? But I'm going to have you find something else, so hang tight. Okay, we're back. Now, don't forget f of x is still 3x minus 7, and g of x is still x squared plus 2x. This time around, I'm going to have you find something different. This is the function value that I want you to find this time. F minus g at 4. Okay, this will be done quite similar to the previous problem. Basically, the only difference is, well, it's not f plus g, but it's f minus g. And also notice that your input value is 4. All right, so this is going to be the following. Take 4, plug it into f, and then subtract what you get when you take 4 and plug it into g. All right, so let's see if I can show you how this works out. When you plug 4 into f, it looks like 3. Excuse me, let me see if I can use yellow here. Okay, so we take 4, plug it into f, so it'll be 3 times 4 minus 7, and then don't forget we have to subtract. Let's see here. Just trying to get the right color. All right, got it. So we're going to subtract what we get when we plug 4 into g. So it'll be 4 squared plus 2 times 4. All right, cool. Let's continue working. This arithmetic turns out to be 3 times 4, which is 12, minus 7. We have to subtract this time around what we're going to get when we when we plug 4 into g. The 4 squared is 16, and then 2 times 4 is 8. Now we have to be super careful here to subtract all of g of 4. So you may want to put parentheses here because we have to subtract the result. Maybe I should have put parentheses in the previous line as well. So be very careful about those parentheses so that we remember to not make a sign error there. All right, so 12 minus 7 is 5, minus 16 plus 8 is 24. Cool. So then 5 minus 24 is negative 19. This is the answer. This is the function value. When you plug 4 into this difference function, f minus g is a difference function, and when you plug 4 in, you get negative 19 out. Okay, everybody, so f is still 3x minus 7, g of x is still x squared plus 2x. This time around, I want to know if you can find f times g at 3. So again, this is you finding a function value. This time around, 3 is your input. Notice that you're plugging 3 into a product function, f times g. Now, I'm going to challenge you to pause this video right here, try this out on your own, and then I'll check back in with you in just a few seconds. So go ahead and pause the video, give this a shot. Okay, so let's see how you did. When you plug 3 into f, it looks like this. 3 times 3 minus 7. That's a little sloppy, but 3 times 3 minus 7. Now, that's what I get when I plug 3 into f. I also have to plug 3 into g, and that would look like 3 squared plus 2 times 3. Again, excuse my sloppy handwriting. All right, so let's keep going. You get here, I'm going to skip a little bit of arithmetic here. 3 times 3 is 9, and 9 minus 7 is 2. And so it's going to be that result times, 3 squared is 9, 2 times 3 is 6, so it would be 9 plus 6, which is 15. So we can see that 2 times 15 is 30. 30 is the answer. I hope you did well. 30 would be your output, your function value, and 3 is your input. Let's do this one more time. Okay, everybody, the same two functions we've been dealing with. This time around, this will be the last kind of example like this. Please find f divided by g at -5. F divided by g is a difference function, and you are plugging -5 in. All right, give this a shot. Please pause the video, give this a shot, and I'll check in with you in just a second. All right, we're back. You can see the solution here written out for you. So we're plugging -5 into f, that's going to be your numerator, plugging -5 into g, and that'll become your denominator. When I plug -5 into f, 3 times -5 minus 7 is -22, that's my numerator. When I take -5, plug it into g, it's -5 squared plus 2 times -5, that is 25 minus 10, which is 15. The final answer is -22/15. Good job. Okay guys, here we go. Example number 2. Same two functions. This time around, we are not going to find a function value, but we are finding a function. Okay? It's very important that you differentiate between example 1 and example 2. Example 1, they gave you an input, you had to find the output. They gave you an input, you found the function value. In example 2, they have given you two functions and they're going to ask you to find a function, okay? Let me add the instructions for you. Give me a second. All right, everybody, this is these are the instructions. Find each function and state its domain. All right, here we go. The first function I'm going to have us find is the sum function f plus g at x, okay? Basically, I'm asking you to operate on these two given functions f and g. You know what f is, it's 3x minus 7. You know what g is, it's x squared plus 2x. So then what do you get when you take those two functions and add them together? Now, I hope that you find this really, really straightforward. When I take f, 3x minus 7, and I add that to x squared plus 2x, it basically looks like that. I'm just adding these two functions together, and it kind of just looks like you adding algebraic expressions together, and that's really what it boils down to. And you know that you can only add like terms. I'm going to underline the like terms for us. You can probably see them. 3x and 2x are your only like terms, so those are the only two terms that you can combine. So then the sum function would be x squared plus 5x, that's 3x plus 2x, 5x, and then you have a minus 7. So this is the sum function. This is the function that you get when you take f and g and add them together. Now, as far as its domain is concerned, what kind of function is f plus g? What kind of function did we get? You can see it's x squared plus 5x minus 7. It's a quadratic function. I'm going to put capital D for domain, if you don't mind, instead of writing out the word domain, D for domain. We studied quadratic functions extensively, I believe, in chapter 1 in our course. And we learned back in chapter 1 that all quadratic functions have a domain of all real numbers. There's a few reasons for that. Back in chapter 1, we said that these parabolas branch out indefinitely to the left and to the right. They forever get wider and wider and wider, so the domain is all real numbers. I can also explain it this way. Any real number input will produce a real number output, so the domain is all real numbers. Great, you found a function. Okay, now don't do anything else with this. That's all they asked you to do is to find a function. Okay, let's find another function. Okay, let me see if I can move this whole page up a little bit. All right, the next function I want you to find. Now let me set the stage once more for you. Give me a second. Okay, dealing with the same two functions here. This time around, I want you to find the difference function, f minus g at x. Find this function. You're going to have to be extra careful with this difference function. So let me play this out for us. So here is f. It's 3x minus 7. And what we need to do is subtract from this function, function g. So let me see if I can show you. What we want to do is minus or subtract g of x, which is x squared plus 2x. Please notice my use of parentheses here. The parentheses here are really important because it will hopefully encourage you to distribute that subtraction sign and then add the opposite. So this turns out to be, removing the parentheses, 3x minus 7, and then minus x squared minus 2x, okay? Again, notice your like terms are 3x and negative 2x. So your final answer here is negative x squared plus 1x minus 7. This is, again, a quadratic function. This is the difference function. This is what you get when you subtract g of x from f of x. Because it's a quadratic function, the domain, again, is all real numbers. Okay? Okay, guys, let's continue working. The same two functions, f and g. You're probably really familiar with f and g by now. I had you operate on these two functions. In the first one, I had you add them, and then I just finished asking you to subtract one from the other. You could probably feel what's coming down the pike now. I want you to multiply them together. In other words, I want you to find this product function. Why don't you pause the video and I challenge you to find this product function on your own. Again, I'll check back in with you in just a second. All right, everybody, I hope you did pretty well. Let me see if I can show you how this looks. So we're going to take function f and multiply it by function g. All right, so function f, remember, is 3x minus 7. And function g is x squared plus 2x. Some of you are familiar with multiplying two binomials. You even say, let's FOIL this out. You know, you FOIL. If you've never heard of the word FOIL, don't even worry about it. It does stand for first, outer, inner, and last. It just tells you how to distribute when you multiply a binomial by another binomial. I'll actually show you how we are distributing. So first we're going to do 3x times x squared. That'll give us 3x cubed. And then also 3x times 2x will give us 6x squared. And then now let's distribute negative 7 into the binomial. So negative 7 times x squared and negative 7 times 2x, like that. So then we will get negative 7 times x squared is negative 7x squared. And then negative 7 times 2x will be negative 14x. Very good. All right, combining like terms. Hopefully this feels really natural for you. You can see that these two are your like terms, and so those are the only two terms you can combine to give you your final answer of 3x cubed minus x squared, minus 14x. All right, this is the product function. Now, this is what we got when we multiplied the functions together. What about its domain? Now, we graphed this polynomial function, or this kind of function, a polynomial function, in chapter 2. And we studied polynomial functions. We saw that their graphs are these smooth curves that go forever to the left and forever to the right. You can look back over your notes over what we talked about in chapter 2 with end behavior. And so this graph will go forever to the left eventually and forever to the right eventually. In other words, any real number input will produce a real number output. I'm trying to convince you that your domain is all real numbers. If you have a polynomial function, your domain will be all real numbers. Okay, guys, I got one more example like this for you, so hang tight. Okay, our two functions, again, f and g. This last time I want you to find this quotient function f divided by g at x. All right, so you can see what we're going to have to do is take our two functions and divide one by the other. You're actually dividing f by g. So you're going to have f of x in the numerator, and you will have g of x in the denominator. Okay, now you're basically done unless this function can be simplified further. Now, this function can be simplified only if there's a common factor between the numerator and denominator. But unfortunately, or I guess it's unfortunate, I don't know, the numerator is prime, 3x minus 7 does not factor. And the denominator, x squared plus 2x, it does factor. It factors with an x. I can show you the common factor is x, and if you factor that out, you get x times x plus 2. But even in its factored form, this denominator does not share a common factor with the numerator. So we were actually done. You can write the final function like that, or you could have just written it as 3x minus 7 over x squared plus 2x. Up to you how you want to write this. We tried to factor that denominator. I'll put the word or here. Either one of these is fine. We factor the denominator only to see if there's a common factor that we can between the numerator and denominator that we can divide out, and there's not. So this function, it is what it is. It's just 3x minus 7 over x squared plus 2x. Now, a word about its domain. The domain in the previous three have been all real numbers, but it's different here, okay? So let me move this screen up a little bit here. Now, for this function f divided by g, we know that the denominator cannot be 0. So let me write that out for us if I can. Hopefully not too sloppy here. The denominator must not be equal to 0. And we know why, correct? If the denominator is 0, then the whole function is undefined. Now, the denominator is x squared plus 2x. But you know what? I'm going to take the factored form of the denominator better. So this denominator here must not be 0. That is to say, each of these factors must not be 0. That is to say, x must not be 0. And x plus 2, the other factor, must not be 0. If I continue solving the second factor for x, subtract 2 from both sides, and you can see then x must not be equal to negative 2. So notice these two statements here. X cannot be 0, and x cannot be negative 2. If x is 0 or if x is negative 2, that is to say if you plug in 0 or if you plug in negative 2 for x into this function that you just found, then this whole function will be undefined. So the domain in words will be any real number except negative 2 or 0. Any real number except negative 2 and 0. That is, negative 2 and 0 must be excluded from the domain. In interval notation, in interval notation, that would be from negative infinity to negative 2, union from negative 2 to 0, union from 0 to positive infinity. I know that's kind of long, but that's basically our way of saying any real number except negative 2 or 0 in interval notation. Okay guys, we finally reached the last example under this objective of combining functions, okay? So finally we have a couple different functions. P of x is equal to x minus 3, a linear function. Q of x is equal to the square root of x plus 4. This is a radical function or a square root function, you can say. All right, what we're going to do is find a couple of functions here and state its domain, all right? So the first function I'm going to have you find is a difference function, and it'll be p minus q at x. So this is very similar to what we were doing earlier, just with different functions. Now, we're going to take p, which is x minus 3. To be really clear, I'm going to use parentheses here. I might have failed to use parentheses earlier, but it's always safer to use parentheses. So there's p. I am going to subtract from it function g, which is the square root of x plus 4. So that's what p minus q at x looks like. All right. Now, you can see, hopefully, that there's no way to simplify this any further. So I'm just going to I'm going to clean it up a little bit, get rid of these parentheses. We don't need them. And just box this. So there's the function. I know it may not look pretty, but it is what it is. It's x minus 3 minus the square root of x plus 4. Now, we want to talk about its domain. Now, when you look at function p, I'm going to draw your attention up here. Look at function p. Function p up here is a linear function, therefore its domain is all real numbers. However, function q up here, guys, function q is a square root function, and so we have to be careful about its domain. So let's have a conversation right now about the domain of q. I'm going to move this up a little bit, okay? When you look at this square root function, I want you to focus on the radicand. When I say the radicand, I mean the expression that is underneath the radical. I just highlighted it for you. Now, we know that the radicand, the expression underneath that square root, must be positive. Well, why? Well, because if you take the square root of a negative number, you'll get imaginary solutions. And so we want to stay with real number inputs and real number outputs. So what we want to say is that expression underneath the square root, when we say it must be positive, really what we're saying is it has to be greater than or equal to 0. That's how I say that the expression must be positive. I don't want just strictly greater than 0. I want greater than or equal to 0 because I can actually evaluate the square root of 0. The square root of 0 is just 0. So we want to say x plus 4 must be greater than or equal to 0. Now what I would invite you to do at this point is to solve for x. Subtract 4 from both sides of this inequality to find that x must be greater than or equal to negative 4. With that being said, I can see that the domain for this function that we found must be the set of all x values that are greater than or equal to negative 4. So we're going to say from negative 4 to positive infinity. This will be the domain for that function. I hope that was clear. Okay, guys, this last one will wrap it up for us. Same two functions, p and q, and the function I want you to consider finding is q over, or q divided by, p at x. Now let's not forget we want to find this function and also state its domain. I would challenge you to give this last one a shot. Maybe consider pausing the video and try working on your own, and I'll check in with you in just a second. Okay, everybody, I hope you put q of x in the numerator and p of x in the denominator. And so this function is done. We found it. So I'm just going to box this here, and there we have it. Now, let's talk about its domain. Okay, so we have a few things to consider when we talk about the domain of this function. Let me move this up just a little bit here. There. Now, when we talk about the domain, can you focus your attention on the numerator, please, only? We just finished talking about this a minute ago. The square root of x plus 4, we have to make sure that that expression underneath that square root is greater than or equal to 0. For the same reasons as as before in this video. We already solved this inequality. We said that x has to be greater than or equal to negative 4. Okay, so as it stands already, our domain must include x values that are only greater than or equal to negative 4. But in addition to that, notice that your denominator, which is x minus 3, let me rewrite that a little neater there. Your denominator, x minus 3, must not be 0. We know why. Because if it is 0, then the whole function is undefined. I am solving for x here. So we can see that x must not be equal to 3. With both of these conditions together, we see that the domain must include values that are greater than or equal to negative 4 and at the same time not 3. So with those two things, statements together, we're saying that the domain is from negative 4 and anything larger than it, except at 3 you must exclude 3, so I put a parenthesis, union from 3 to positive infinity. So the domain of this function would be any real number greater than or equal to negative 4, excluding 3.